All right, thank you very much. So I would like to thank the organizer, of course, for inviting me here. And my name is Karol Nass, and I'm a postdoc at the Max Planck Institute for Medical Research in Heidelberg. And I will be talking about rapid data quality feedback and online monitoring using CASS, the other program that does almost the same thing as Cheetah. But before that, I would like to repeat some of the introduction to serial femtosecond crystallography so that you keep this in mind all the time during this workshop. So the features of serial femtosecond crystallography are that every exposed crystal is destroyed, and therefore numerous shots of different crystals with possibly different sizes need to be recorded, and there is no control over crystal orientation in the jet. Also, the crystals stand still during typically 40 femtosecond exposure, because there's simply no time to rotate the crystal at velocity lower than the speed of light, and therefore only part of the reflection intersects the eval sphere, which results in a partial reflection, which I'm sure Tom will be talking about. Also, if you have questions, you can ask him or James Fulton. They are the experts on that. And it's very good that they are here. And because of the finite small crystal size, we are talking about nano crystals, and there will be fringes around black spots. And you can see a simulation done by Wolfgang here. You can see the fringes between the black spots for a 6 by 6 units a crystal, as compared to the crystal that had 200 by 200 unit cells. And in addition to all of that, crystals in the jet may be hit by the center of the X-ray beam, or just grazed by it. It happens just by chance, so there's no control over that. And also the beam intensity and the spectrum, as this has been said before today, varies from shot to shot quite a lot. So the X-ray pulses aren't all the same, which adds even more variations to the already not so well controlled crystallography experiment. And you can see here the per shot variation in photon energy and intensity of the pulse of the X-ray pulses. These are per shot spectra coming from the SASI shots. And this variation comes from the principle on which the SASI FEL operate. And you see that the position of the X-ray energy jitters quite a lot, left and right, and also the intensity of the pulses are different, and also they have these very nasty spikes, which we don't really know how to deal with them. And here you can see histograms from few thousands of shots, histograms for electron bunch duration, which corresponds to electron bunch duration translates to the pulse, X-ray pulse duration. So the variation in the electron bunch duration also leads to variation of the X-ray pulse duration. So not only intensity and spectra varies, but also the duration of the pulse length varies and per shot. And here is the average of few thousand shots for the photon energy. You see there's a distribution of the mean photon energy as well, so you have to include that into your calculations. And also the pulse energy, so the intensity in millijoules, this also varies from shot to shot. Here's the histogram from few thousands of shots. But despite all of the variations in the parameters that affect the measured intensities from your experiment, as it has been shown, as John said before, if all of them are independent, if all of the variations are independent from each other and random, and if there is no systematic error in there, the arithmetic mean of a sufficiently large number of measurements or observations will approximately correspond to the true and fully integrated reflection, which in our case is called the Monte Carlo integration. And the Monte Carlo convergence displays 1 over square root of n convergence, which means that quadrupling the number of observations halves the error. And if you take the R split here on this axis, if you take the R split as the measure of the goodness of your data set and calculate it for different number of indexed patterns or images, you see that, for example, for 4,000 images, you get an R split of 10%, and quadrupling it, so if you want now quadruple it, you get 160,000, you almost reduce your error by half, which is following this 1 over square root of n convergence, and the points are cut in B data, and the line is the fit to these data points. So this explains why in this Monte Carlo method we need so many images, and to efficiently analyze all of them, because it's a lot of gigabytes and terabytes of data, we can use also CASS to do that. And CASS stands for the CASS ASG software suite, which is now developed mainly by Lutz Fokar from our institute. And the features of CASS include that the CASS is used to correct and combine and analyze correlated data from each shot. And also another feature is that multiple threads are parallel processing of all of these data. And that the analysis is based on very structured and easy to understand ini file architecture, and into that ini file you can put what to do with predefined functions, which are explained in the documentation over here, so that you can build your own analysis pipeline, whether if you need something specific to do other than find crystal hits. So using CASS on SSX data, one of the main features and very useful features is that CASS can be used on the online data stream. So during the experiment, before you have recorded, before the data has been stored on the disk, so you can get online feedback from your experiment. For example, if you want to find crystal hits, of course. And you can do that on the online stream and calculate on the hit rate on the fly, which is very useful for jet alignment. So every time your jet with crystals move out from the position of the X-ray beam, your hit rate drops down, and then a beamline scientist has to move back the jet to the position where the X-rays are, and then increase the hit rate again. So that is useful for controlling the experiment. You can also accumulate the virtual powder pattern to check for the data completeness. You can also check the pixel overload online, not after the run has been saved, and so you can know that before it and adjust it very quickly. You can write an analysis that checks whether some kind of criteria have been met. For example, you can ask whether the pulses were seeded or not. And you can also obtain the time delay which we have used, obtain the time delay of the palm laser using the raw time tool data, which has been recently implemented also at CXI. And in offline, so for example at home, on the XTC files that Anton explained what they are, you can do exactly the same and also write the data to HTF5 format or to CPF format for our recently released Nano XDS version, and try to analyze them with that. So here is what the online data analysis using CASS looks like. And here we have the graph of the online hit rate, which grows with time whenever we are on the jet and have enough crystal concentration. We can also monitor the X-ray beam energy and the fluorescence signal, or calculate the radial distribution of intensities of this virtual powder pattern. And also we can look up the last crystal hit, which is very useful. And we have also used CASS to analyze other types of data, which include the SACS and WACS radial intensity profiles, and fixed target diffraction images, and single particles, for example viruses from the aerosol injector. We also analyze the fluorescence signal from a fluorescence detector, and analyze the X-ray pulse spectrum, which is useful for seeded pulse identification. And we calculated the palm laser delays from the raw time tool data. So self-seeding at SCRS may lead to a possible improvement for SFX, as it has been said before. And you see that the SASE spectrum has a quite large bandwidth, and the energy and the mean photon energy fluctuates a lot. So by using self-seeding, the bandwidth of the X-ray energy can be reduced quite significantly. So that would reduce one of the errors in SFX. But actually, how really seeded is the seeded pulses, and does it really improve the SFX results? So here are some of the spectra of the seeded pulses that we obtained from the CXI spectrometer and analyzed with CASS. And you see that not all of the pulses are perfectly seeded. We have identified at least three classes of pulses based on the analysis of the spectra. And some of them are nicely seeded, some of them are more or less seeded. The intensity of this peak is much lower than this one. And some of them are also not seeded. And we carefully selected, based on this strict criteria, the best seeded pulses from the experiment, and indexed the crystal hits from those pulses, and calculated some statistics using crystal. And here they are presented in the table. So we had around 8,000 indexed seeded shots. And for comparison, we have randomly selected also around 8,000 SASE shots. And you see that the improvement between SASE and seeded isn't very high. I would say, in terms of these statistics that were used for comparison, like R-split or CC1/2 or I over sigma, those two data sets are almost the same. And here, for example, is a plot of R-split versus resolution. The blue and yellow curves are coming from this seeded and SASE cases that had the same number of index images, so the lines are almost the same. And here for comparison is the whole SASI dataset, which consisted of 57,000 index images. And so it's much better because of the Monte Carlo convergence. And now I would like to show some other SFX results. So the first new structural information obtained from LCLS, from the SFX data, from CADB crystals, which were crystallized in vivo and phased by molecular replacement. And in this case, the data was good enough to strongly reveal the new part of the structure, which wasn't known before for this protein, the propeptide, which is here shown in green. So this is the data directly after molecular replacement, and the FO-FC map is shown in green. So we could easily build in the model of the propeptide into that map. But this was phased by molecular replacement. But what about the novel phasing in SFX, which was the question for a long time? So for the test case, for the novel phasing from SFX data that suffers from many sources of variations, we wanted a really strong anomalous signal and something that scatters really well. And we chose lysine gadolinium for the test case. And the anomalous signal from gadolinium, even in the pessimistic case, where more than 60% of the gadolinium atoms are disordered, still gives about 10% contribution to the scattered intensities at 2 angstroms. So it's a very high anomalous signal. And we have demonstrated that the novel phasing works using SFX data, which tells us that SFX can deliver intensities of that are sufficiently accurate for phasing. But despite the very strong signal, we needed 60,000 images to phase the data, and it only worked using this many. We couldn't make it work with less images. And if you are interested, you can have a look at this nice review from John Halliwell. Okay. And as it has been said before, the development of detectors and software will make it much easier in the future. For example, when we reprocess the lysine gadolinium data using optimized detector geometry, we have found we could improve the indexing rate by quite a lot, and also the CC-ANO have improved, and R-split over R-ANO, which led to the possibility of this time automated phasing in Phoenix. So we will try to get to this step tomorrow during the tutorial. And you can clearly see that using the automated structure solution in Phoenix, on this reprocessed lysine gadolinium data, it worked without any supervision. Here you can see the model that was built by AutoBuild and the model that from PTB supposed to it, and the two gadolinium sites where the AutoBuild in Phoenix tried to fit a helix because it didn't know anything about the gadolinium that was there and is complex. So we will try to get to this point tomorrow during the tutorial.